This presentation, actually I'm borrowing it from Jerry Verduff. He did it back for Denver for us. We also had a club there, Denver Radio Club. We would meet once a month and do about an hour presentation each meeting. So we kind of did a lot. But this is going to go through some of the basics. So I'm going to go through, I don't want to clear every chart, but we'll, talk about it. So, the basics are, we know the sun influences radio propagation, okay? And that's beyond what they call ground wave and line of sight. So people know what ground wave and line of sight are. Basically, your HT is line of sight. If you can see the antenna, you can talk to it. If you can't see the antenna, you can't talk to it. Usually that's how it works. Ground wave are signals that travel along the ground. Especially great on the ocean. You can go hundreds of miles on the ocean with very little power because you have that nice salt air and salt water and flat surface. So those are the two biggies. Ground wave also works, on the ground as well, not just water. And as we know, or you may know, conditions vary during the day. Certain things happen. They call on the gray line. You'll hear that term every now and then, and that means it's right before sunset and night, or right before night and sunrise. There's this gray line, and usually, as you would expect something like that, it works vertically. So it works from North America to South America, or maybe North America to South Pacific. So it works in that line. It's not going to work to Europe, but it's going to work vertically because you guys are running right where the propagation layers are starting to fall apart because the sun's coming up, or they're starting to be created because the sun's going down. Reflection, that occurs at boundary points. So we'll talk about that. I have some examples of that. And that radio waves are reflected by mountains, by suns, by vehicles, by trees, by buildings, everything else you can imagine. And also affected by temperature and moisture content. So sometimes a nice rainy day you get better coverage than you will on a dry day. Again, some radio energy is absorbed by the medium it goes through. So when you go through a layer, not all of it gets brought back down again. Some of it disappears in outer space. So you're going to be dealing with that type of thing. Refraction is really what's happening when you're dealing with HF frequencies and you're dealing with the ionosphere. You're not reflecting, you're refracting. It goes up and then it curves and comes back down again. And I'll show you an example of that. Bending occurs when the waves hit different speeds. So different things absorb and refract at different speeds. Just like if you look at a light going into water, like a glass of water, sometimes you'll see the light bend. That's bending. And the amount of bending increases at the higher frequencies. So you've got to take that into consideration. The speed of waves through the atmosphere change, again, density, ionization, and HF bands depend upon refraction. VHF, UHF, line of sight, or ground wave possibly, but HF is all about refraction. And I guess we can see this. So basically this is what they're talking about, refraction. You have a station here, actually I can do it this way. Come on. Well, hitting the wrong button. There it is.
That's the red button.
No, it's not right enough. So basically, your station's on the left and your actual path's on the right. If the wave wasn't bent, you'd have that sky wave going up, hitting the atmosphere, and it curves and bends back down again. If that ionosphere wasn't there, it would just keep going out into space. So you can talk to space. That's why a lot of the communications with the shuttles and the space station are all VHF, UHF, or higher band HF, like 6 meters, because anything more than that is going to refract back down again. You're never going to hit it. So that's why most of the stuff is that way. The ionosphere affects frequencies below 30 megahertz, so basically everything below 6 meters, everything lower than 6 meters. So, basically in our case, it's from 28 down, 10 meters down. 30 to 260 miles above the Earth's surface is where the ionosphere sits. It contains free ions and electrons, so there is some electromagnetic work that's going on there with taking those frequencies and bouncing them back down again. And again, it's very key with the ultraviolet radiation, and that's why they talk about sunspot cycles and solar cycles having an effect on communications. So I missed the last really big one because I didn't get my license till after it, and they've been kind of dud since pretty much. This one really was, and we're hoping they're not going into a dry spell. Skip distances. Now, remember we said that you refract, so your signal goes up in the air, and it bends on the ionosphere, and it comes down, and it hits Earth, or it hits the ocean. What's it do? It bends and refracts back up again, and it bounces and comes back down again. And just to throw something out there, every time it refracts, it changes polarization. So if you have a dipole antenna, you're going up horizontal, it hits the ionosphere, it changes to vertical, comes back down again, hits the Earth, refracts back horizontal, goes back up again, and so on. And that's why HF isn't as critical to how you have your antenna as it is with VHF and UHF. Mainly because we're dealing line of sight and we're dealing with a repeater site, which is usually vertical. Skip distances depend upon the frequency. You'll hear a term called maximum usable frequency, MUF. I'll talk about that in a few minutes. And then there are several layers of varying distances of varying heights. So again, it depends which section of the ionosphere you're dealing with, because different ones deal with different frequencies. So the further up you go, obviously the longer your shot's going to be. So here are the layers. And basically the ones we care about are DE, F1, F2. And the lowest is obviously the D layer. It's about 50 miles up. And it acts like an RF sponge. It just sucks in your RF. So during daylight hour, it basically dictates the LUF, which is the lowest usable frequency, as opposed to the MUF, which is the maximum usable frequency. The E layer is about 70 miles. It only is there during the daylight hours. When the sun stops heating the ionosphere, the E layer goes away. So it isn't useful it isn't there at night, it's only there during the day. Same thing with the F layer. During the day, there are two of them, F1 and F2. At night, there's just one, F. And that's anywhere from 90 to 250 miles up. And then the F1 is not as important to propagation in the medium bands. The F2 region is really primarily what supports HF communications. And at night, they combine into one layer. So that's why at night, sometimes your reception's a lot better than it is during the day. For those who've listened to AM broadcast years ago, I used to listen. I used to pick up, I lived in New York City, used to pick up stations in the Midwest. Those Class A clear channel stations. Yeah, I pick up the ones from Chicago or
Salt Lake.
Yeah,
Nebraska.
all over. I used to get QSL cards too. They used to have them. Yep. This is kind of a representation. You can see from the Earth, it's up about 50, 75, about 110 is F1, and then 200 miles above is F2. And you can see around there how they separate out during the day, but at night when the sun stops heating them, the F combine into one. And a lot of the other ones, the D and E, kind of disappear at night. So type of propagation, we have ionospheric waves. So that's what we call sky waves. It hits the ionosphere, bounces back down again. So it leaves the antenna at an angle, it goes up at an angle, comes back down, and keeps bouncing back and forth, until it hits another antenna and keeps going, but usually they'll pick somebody up. There's tropospheric waves, and this deals with the radiation that runs closer to the Earth, the troposphere. And this works for the higher frequencies, like you'll see it some on 10 meters, a lot on 6 meters. People say, wow, 6 meters is open, I got, 1,000 miles. You can even get on, if it's good enough, you can even do it on 2 meters. You can talk hundreds of miles on 2 meters. Because what happens is the troposphere sits below the ionosphere, it's just above the Earth, and it's like a duct. So just like in a house for air, with your heat, the signal goes in there and just flies through it and comes out somewhere else. You may not hear anything in between. Won't hear you, but at the other end of that duct, they'll hear you.
Tropospheric ducting is a real popular thing to do between Hawaii and Southern California. It actually gets up into the UHF bands on really good conditions.
Yep.
Also for television.
Yep.
You should use UHF, tropospheric ducting, yes.
Mm-hmm.
But I was in on a hot summer day, I could pick up.
Yep. That's what it takes, those nice hot summer days.
Yep.
I've talked to
Does
Hawaii
it have
too.
anything to do with,
Yes, side down.
Yeah.
When it comes to it, what you're not being.
does the length of your antenna or the build of your antenna have anything to do with that thing?
No.
No. You
Just, it has to do your efficiency of your antenna. It's
Okay.
going to have to do with, but as far as,
No, I understand it's this skyway.
always the bigger antenna, the better it is, type deal. But the signal goes out, it'll still go out.
Yes, sir.
Yeah. The only issue is how far the antenna is, like a dipole, is above the Earth.
Okay.
Otherwise, you get into something called a near vertical incident antenna, and we'll talk about that some other time. But that doesn't use ground wave. That goes up and it comes down like a cone. So we talk about troposphere, we talk about ground waves, which are surface waves. This stuff runs along the surface. It's affected by the surface, so it could be the ocean. It's usually vertically polarized, and the absorption increases with frequency. So the higher the frequency, the shorter the distance, because you're going to lose less of that signal as you go along. And of course, like we said, it travels much further over water than it does over land.
With the vertically polarized, you have a dipole, raise it higher so the elevation pattern is lower? And run ground wave?
I don't want to go into that, but basically, when you have a vertical, it depends on your incident angle, what angle your antenna, your signal comes off the antenna at. Usually vertical tend to be a higher angle, so they're shorter hops, so there's a bunch of shorter hops, and each hop you're going to lose some of your signal. A dipole tends to be more of a lower angle, so you get a good shot on the first, and then usually you hit Europe in like 2 or 3 shots versus 5 or 6 with a vertical. So it kind of, that's kind of the difference between them. But people talk about verticals. I've used one, it works well, and then people say a vertical operates poorly, equally on any frequency. In all directions. Yeah, transmits in all directions, equally bad. So, it's.
But they work.
But they work. Yeah.
That's all I have.
And if that's all you can put up, I'm running a long wire, which is pretty much on an angle. It's almost a vertical. Whatever works, works.
And they hide nicely in a
Yeah.
in a flagpole.
Yeah, there are people who live with covenant restrictions. They put them in flagpoles. I know someone ran a vertical next to his house. A lot of them get one of the better antenna tuners and mount it at the base so they get maximum transfer power to their antenna. But that's a totally different subject, and we can talk about antenna tuners some other time. I have presentations on that too. All I get steel. So the blessings of skywave, again, the medium for most of us is below 30 megahertz. That's where 10 meters is where you start getting the skywave. And the ionosphere refracts a radio wave and returns it back to the Earth. The maximum usable frequency, and that's a function of how highly ionized the F region is, okay? So the higher ionization, solar spots, solar storms, you get to a point where it's more active, it bounces more signal back. And again, the higher, and it lets you go higher the frequency. The lowest usable frequency is a function of the absorption. Below a certain frequency, most of it gets absorbed by the layer and doesn't get refracted back. So that's the two, so you operate within the range. And we'll talk a little bit, because those numbers are kind of published. You can find out what those are. There are a lot of websites that provide that information. And again, it correlates with movements of the sun. It peaks at noon and then drops back down again. So it kind of, that's why we said kind of that shadow period at night tends to be fun. You can hit some people that are going into night, some people that are going into sunrise. There's a lot of good times to hit. But the main inhibitor is the solar cycle. That determines how active the sun is, how much radiation, ultraviolet radiation, magnetic radiation the sun is throwing out. Solar cycles run about a little more than 10 and a half, almost 11 years in length. There's a solar maximum in the middle, solar minimums on the end. And during the maximum, it refracts signals up to 40 megahertz. So now you're talking about almost close to 6 meters. At minimum, you're lucky if you can get out at 20 megahertz.
Yeah.
Okay, so that's, and we're currently in a downward cycle of 23, which, let's see, is that where we are now? Yeah.
Yep.
So and we're way in the downward cycle at this point. So here's a kind of example of your 100-year cycles. You look back from 1940, you look at 1960, man, they still talk about that one. And even 1980 wasn't bad. But then as you start going, you can see we're right here, so we're right coming down to the low spot. I think they're very optimistic about 2020. I'll believe it when I see it, because there's discussions. There's so many discussions on this because the information is still trying to figure out what it means, and we don't know if we're going through a period where actually the solar minimum for decades, where the solar cycle will actually be kind of stunted, like this year was.
It's gonna happen.
So we'll have to see. Solar radiation, X-rays, ultraviolet, extreme ultraviolet. During solar flares, you have the ultraviolet and the X-ray emissions increase, and they cause HF signal loss. X-ray flares are small, medium, and large, and they're measured in an angstrom range, which is just a measurement of X-ray frequency. And we'll talk a little bit about what the numbers mean, because you can find the numbers at any given time. This is kind of hard to read, but it's kind of showing the sun, and a flare produces magnetic storms, and they take about 20 to 40 hours to reach the Earth. Electromagnetic radiation takes about 83 minutes. So if there is a magnetic storm, there are differences on how long it takes. Cosmic rays take about 15 minutes to several hours. So they kind of vary on how long it takes something to hit us. And it's kind of neat now because there are some really good satellites that are watching the Earth, watching the sun. They're actually watching the whole sun. So they can see a solar storm on the backside and predict when it's going to come around. And we've been lucky; we haven't hit a major flare that hits up the Earth. Most of them have been before or after, but at some time one's going to hit. It's going to make a mess of things. Okay, so now we have the solar indexes. So the big number is the flux, and that's a measurement of the radiation, solar noise. And it's emitted at about 2.8 gigahertz, or 2,800 megahertz. The SFU, it equates to ionization in the F2 layer during the day, because remember, since it's based on the sun, it's only going to happen during the day, when the sun is facing where we are, where we care about. So it's a good indication of the HF conditions. Remember we said F2 is really the primary layer that we use during the day. And the units run from about 50 to a high as 300. So low values indicate a low maximum usual frequency. So a low number means that the MUF is going to be maybe 20 megahertz, somewhere in that range. A high value is going to indicate maybe 30 megahertz, higher, 10 meters versus 20 meters. And there's a sunspot number. And this is a smoothed number, which means they kind of average how the sun has been going over a period of time. Usually it's months. And it talks about the amount of sunspot activity, the level of activity. Has the sun been pretty quiet? Has the sun been pretty active? So it's calculated using 6 months of data before and 6 months of data after the desired month. Now I always wonder, how do they find out what the 6 months are going to be like going forward? And basically they just interpolate it based on what it's been like the previous 6 months and where we are in the cycle. So they kind of can say, okay, way we are, we're kind of coming down on the cycle, it's probably going to get worse, so probably the next 6 months aren't going to be as good as the last 6 months. So they come up with that number. And this varies from 0 to 200, with obviously an average of 100 at maximum. High sunspot numbers are best for HF propagation, and low sunset numbers are best for low frequency propagation. So, 160 the lower bands. Or if you're into the real low stuff that we have access to now, that's the place to use it. So here's just a picture of a sunspot. This was taken NSO Sacramento Peak Vacuum Tower Telescope. But the one to look at now is just the solars, and the other satellites have fantastic pictures. And that's all on the NASA website. So we talked about sunspots, now we have coronal mass ejections. So that's usually what comes out of a sunspot. When a sunspot gets very active and the waves come up, the magnetic waves come up and they burst and release all that magnetism and all that flux out into the atmosphere, or actually into space, usually in our direction or near our direction. So you have high particle emissions, protons, alpha particles, and they cause high absorption in the polar regions, which is why you get the aurora borealis or the aurora australis, if you're in the southern hemisphere. Low particle emissions cause magnetic field disturbances, so if they're not too bad, you'll still get some field problems. Sporadic E, though, which means you'll get that tropospheric kind of effect a little bit, where you'll get the E layer open up and you'll get some 50 to 144 megahertz. You can actually talk on an HT out to Hawaii. You can get a shot right through. And transequatorial spread F. Now this kind of runs along the geomagnetic equator, so it doesn't affect us too much, but it allows for long distance communications that are equidistant from the equator. So basically, if it wouldn't work down to Hawaii unless you were on the same latitude as Hawaii. So this is basically communications across the same latitude, the same equidistance from the equator. And again, this is a result of intensified F2 layer, which is high sunspot activity. And actually, signals have a rough aurora-like note. They kind of go in and out, and they kind of make some weird sounds. So you can definitely tell you're doing it. This is a little important because you start seeing these numbers. So there are natural variations in the geomagnetic field, and that's what our signals are, is electromagnetic. So we wind up with a K index, which is basically, it's a 3-hourly range magnetic activity. So you're looking at And again, it says quasi-logarithmic because it kind of goes up on on an angle, like a 90-degree angle. Or no, sorry, 45-degree angle. So it ranges with the activity, and it's they assume a quiet day curve, so the K index could be good or bad, and I'll talk about what numbers mean. And then there's an A index, which is daily average of the K index. So K index is what's happening now over an 3-hour range, and the A index is what's happened over the last day. So an A index below 15 and a K index at or below 3 is good for propagation. So that's kind of good to know, and you can see what the K's and A's are. There are even websites that'll put it at the bottom of your browser, little apps that'll do that. But it basically, the key is the lower the number, the better it is for talking, for DXing. And here's kind of a good example. So obviously A is the best because the noise is low, and you're not going to have a lot of atmospheric noise. That's the key. As you get higher in the A's and higher in the K's, you talk about unsettled, active, minor storms, severe storms, and very major storms. And again, this is solar activity and its impact on our ionosphere, on the Earth. And HF band prediction characteristic, 80 and 40 meters are good bands for distance communication, especially during sunspot medium. So they're kind of in that middle there. They're not really low there. So that's, you're talking about 7 megahertz to 40 is 30, no, 14. No, it's 20.
3.5 to 7.
3.5 to 7. There you go. Thank you. 30 meters is greater than 40 at night. Again, the ionosphere cools down and the F layers converge. 20 meters is very popular during the day, but it closes down at night, especially during the winter, the sunspot minimum. So you'll hear 20 meters is real active during the day. At night, it gets dead. And in return, 30 and 40 meters pick up during the nighttime.
It just hit me. This is why there's so many retirees on the air.
Yeah,
It's during the day.
yeah, that's it.
I know.
For those who have the
But again, remember that the sun is moving.
Right.
So different places are going to be during the day and at night. So, that's why things like Echolink and IRP are so nice, because they're irrelevant of the ionosphere. You're talking just local. So it's kind of fun to do that. 15 meters, which is pretty high frequency. During sunspot activity, minimum, a few stations are heard. You need good sunspot activity to get those higher frequencies. 10 meters, same thing. The low absorption allows good communications with relatively low power during daylight.
I find sometimes discussing these things, you're using meters.
Yeah.
10 meters, 30 meters. And yet, many of our young troops are new into the field. And then I realize that 30 meters is actually 10 megs, and 10 meters is actually almost 30 megs. So they're going to get it all backwards. So.
Yeah. As the meters go up, as the meters go down, the frequency goes up because the meters are the function of the wavelength. So, when you're dealing with 2 meters, 144 megahertz is 2 meters.
I just divide by 300 and hopefully it's close.
Yeah.
Happens.
And it makes it easy because most radios these days, when you hit the end of the band, won't let you transmit. But you got to be careful if you're doing upper sideband and you get too close to that end, you could be operating out of band.
That's actually,
It's the other way around on 40 meters.
that's why I got my license.
That's basically it. There's a lot of stuff on the web. ARRL has a propagation page. NOAA has propagation. There's a QRZ solar report. There's EHAM, DX Summit, solar terrestrial. I'll give the charts to Jason, and he can post them. And you guys know we have a Facebook page too?
Don't do Facebook.
I'm not doing it there, but just saying, you know, we're starting to use it more. So,
Can we do these things in the old time?
yeah. So, but that's basically it. That's good. I kind of rattled through that in about half an hour. Any other questions on that? I know it's I try not to get too deep into it, but
That's what you're doing.
it's kind of interesting stuff, and if it sparks your interest, there's a lot of stuff out there on it. You can find it on the internet. And again, if nothing else, go look at the NOAA website and look at the solar satellites. It is so interesting to see some of the pictures they have from those. And the fact that they actually can see around the back of the sun, so they can project when solar storms are coming around. And that's really neat.
That suggests there's a satellite on the other side of the sun.
What was that?
That suggests there's a satellite on the other side of the sun.
Yes.
There is?
Yes.
That's crazy.
Well, we go on the other side of the sun. It just, they're
Yeah.
they're geostationary around the
So
sun.
I mean, it made it there and it just stays there.
Yeah.
That's pretty cool.
Actually, there's two. They're kind of, one just on one side, one on, there's three satellites. So they pick up, each picks up a little more than 30. But it's really slick to look at those pictures. Yeah, the last ones were the latest.
I have a quick question.
Sure.
So I heard this recently, but I would like to hear it
Do
from
it again.
Oh, no. What happened to layer A, B, and C? Now, I heard something, so I'm just curious if anyone's heard the same.
They don't live, they don't exist.
I don't think they really exist.
So the founding fathers of RF decided to start at D because they weren't sure what they're going to come up with.
Yeah.
So they started at D because they weren't sure if they were going to become smarter in the future and find C,
A,
B, and
or
A
C.
closer to the Earth.
Yeah.
So that's why the lowest one starts at D. It was a burning question for me.
Thank you.
I was like, why is it D? That makes zero sense.
Yeah.
D for daytime.
Oh, there we go.